Hello, everyone. Today we are going to resolve this question. This is the question about DC motor. DC motor and the DC motor is shunt connected. This means the armature will be connected in parallel with the field windings. So this is the schematic of the equivalent circuits that illustrates a typical shunt motor. And according to the question, here is the question, right? Take about 1 minute to read through it. Now the question here said, the question say the VT here is about 220. And the question has two conditions. In the first conditions, which is condition 1, the armature resistance is equals to 0.2 ohm. And the field resistance is going to be 220. And the speed is 1000 RPM. So this is the first condition, right? And also do not forget that the total current is 10 ampere. So here, this one here, the index 1 here is to indicate that this is so-called condition 1. In the first condition, this is what we have. We are given by the equations, by the questions, sorry. Now, the second condition is the armature resistance is going to change to what value? 0.2 plus 5. So you get 5.2 ohm here. So these are the conditions. So I better rearrange the text because we don't have enough space here. So now I will try to write everything in one line. So condition 1. IT1 10 RA1 0.2 RF is 220. What else? N 1 is 1000. So these are the initial condition. And condition number 2. RA2 is 5 plus 0.2. So these are the conditions we are going to resolve question. Now, before going on further, right, then it's better for us to revise the concept. Um, the first concept that I would like to bring up is the armature voltage, the armature EMF. The armature EMF is given by this formula, 60A and then 5N. So I guess you guys are familiar with this formula. V here is the total number of conductors, and P is the total number of poles, and A is the total number of parallel paths, and phi is just the flux per pole, and N is uh, this, the rotational speed in RPM. So now the question is, can we rewrite this formula? Now you have the phi here. This phi is the polar flux, right? And we know that the flux is proportional to the field current. So if we substitute the flux into the original formula, then we will end up with Vp over 60A and then MIF and then N. So now, can you see that we have some variable here, some parameter here, but they are fixed. They are fixed in value. During the operation of the motor, they are not going to change because this parameter belongs to the hardware. But the field current may be changeable. But normally, right, if you don't change the supply voltage, and if there is no hardware change in the data, then we are not going to expect any change in the field winding resistance, and therefore we should not expect any change in the field current. So essentially, right, the only thing that can be changed, I will just say this: the only thing that can be changed is EA and N. So in this case, if you are given two conditions, right, maybe right, you can rewrite EA1, which is K. K stands for this value. Yeah, I will write down. This is K. Yeah, K and 1, and then we have another armature voltage, which is specific to condition 2, right? Then we have a K value. The K value will be unchanged. So we can write the equation in this way. And then the speed of the motor. The speed of the motor is still N2. So in here, we may just safely conclude the ratio of the armature voltage is just the ratio of the speed. So this is the characteristic of the shunt connected DC motor. Another thing that we need to pay attention to is this condition. The load torque is going to be proportional to the speed, the square of the speed. So now, if this is the case, we better write this down. right? T is proportional to n squared. But then we have to recall the fact that, oh, by the way, I need to label this equation, right? Equation 1. Otherwise, we have this condition, and then we also know that T omega, which is the power, mechanical power for the DC motor. And if there is no power loss, right, then the mechanical power will be equal to the electrical power. So what is the electrical power? The electrical power should be the electrical power in the armature. In this case, it should be EAIA. So in this expression, we can conclude that T is equal to EA, the armature voltage and armature current, and divided by omega. Now, with this condition, with this concept, we can define two equations for the torque, and the equation is going to account for condition 1 and condition 2. So now we have T1 equals to EA1 IA1 omega of 1. And we also have T2 EA2 IA2 and omega 2. And from here, so we should be able to come up with T1 and T2. And this will be equals to EA1, EA2, and then IA1, IA2, and then omega 2, omega 1. So according to here, right, if I divide T1 by T2, then I should end up with this formula. But now, it's okay if we're going to do for this formula. But now, we have to take advantage. We have to take advantage of what we have derived here. And we also need to make good use of the condition given by the question. The condition is the torque is going to be proportional to the square of speed. So in this case, if you have this condition here, right, so we can say this one, right, this one is actually n1 over n2 square, okay? And how about this one? And this one, according to here, this one, right? It's actually n2 divided by n1, okay? And this one, according to here, is n1, n2, okay? So now we have left IA2 and square. So these are the conditions that you can derive from here. Now, with this condition, right, we should be able to handle all the analysis. The first thing that we need is to simplify this expression. We have n1 divided by n2 here. And we also have N2 divided by N1 here. So essentially, these two expressions, these two expressions are going to cancel off with each other. So finally, what we have here is this one, IA1 over IA2, and then N1 and 2. So these are the conditions we can use for resolving the equation, the question. Now, what is VT? VT is essentially the voltage, summation of the armature voltage and also the voltage across the armature resistance, which is the parasitic resistance. So VT is EA plus IARA. So if we do some rearrangement, then we could get EA VT minus RA. Now we have this equation, right? So in this case, let's try to have a look whether we have anything meaningful here. We can use EA1, which is VT, because the supply voltage is not going to change. IA1, RA1, yeah. We have also EA2, VT, IA2, RA2. And with these two conditions, we can safely say EA1, EA2, which is equals to VT minus IA1, RA1, VT minus IA2, RA2. So these are the things that we can do. And now we can also square it. If we square both sides of the equation, we can just do this. Now, according to here, N1, the ratio of the armature voltage is going to be the speed, the ratio of the speed, the motor speed. Let's write down more clearly. Okay. So now we can say that the right side, the left side of the equation, is EA over V1, right? According to here is N1 over N2. So we can say that this guy, N1 over N2. And then here is T minus E1, VT minus IA2, RA2. Yeah, hang on a minute, right? We have this condition here as well. I mean, according to this equation, this guy is actually IA1 over IA2. Now, everything is clear now. This equation is enough to solve everything. First, we have IA1, and we have VT, we have Ra1, and we also have Ra2. So what we don't have in this equation is Ia2. So now let's solve this problem and see what we can get. Ia1, what is Ia1? We don't have Ia1 here. Yeah? You can work this out. IT1 is equals to Ia1 plus IF. And Ia1, we don't know. And then the field winding, the current in the field winding. So in here, we can say that right, the voltage divided by the field winding resistance, which is uh, VT divided by RF. So this is enough for us to dig into further. So from here, we can say that the current for the total current, yeah, which is 10 ampere. We have already said that the 10 ampere is equals to right, Ia1, and then VT is what, 220. And what is the resistance? 220. So now we can safely conclude that Ia1 is indeed 9 ampere. So we have a few conditions. And now the most important equation is here. I will label this equation 1. And basically we have almost everything. So we can continue here as well. But then we can also erase some space here and then continue. So what space we have here? Yeah, let's erase this corner here. We don't need this corner. Now we have Ia1 and we have this equation. We also have VT, right? We are now trying to substitute all the known kilometers back to equation 1. So in here, Ia1, which is 9, and Ia2 is not known. And then VT is 220. And Ia1 again, 9. And Ra1 0.2. And we can do the same here. And VG minus, and Ia2, this one is going to be resolved. And Ra2 can be found from here. And if you do that, then if you are careful enough, if you are extremely careful, then you will be able to solve this equation. Oh, sorry, I missed the square here. If you solve these equations, then you will end up with IA2 being equals to two value, 6.454 ampere, or 274. But this value is way larger than 10 ampere. So it's not realistic. You wouldn't be able to end up with an armature current much larger than the supply current. So in this case, we can just safely reject this answer. So this is the only answer left. Now you have this armature current, right, which is the answer to the question. And the question also asks for the speed. So how are we going to find the speed? So we have to make good use of um, this formula. That way, we just play around, do some algebraic manipulation. So we will get n1 square and then IA2 divided by IA1. So n1 is 1000 and IA2, which is the one that we get, and IA1. IA1, did we get IA1? Yes, we do. We got IA1 here, 9. So if you are careful enough, you should be able to come up with an answer for this question. And the answer is the second part of the question. Yeah, the speed. The speed should be 852. So this is the speed in RPM. So if you have any question, please leave your message, leave your question in the comment section underneath the video. Thank you very much.